requirement of high voltage for some device, then we will use the step up transformer. If there is a requirement of low voltage for some device, okay, some devices works on low voltage, so there is a requirement of low voltages, but the supply voltage that is coming in your home is something more like 220 volt. Okay, suppose for example, see this part here. For example, in your home the supply is 220 volt, but to run a device there is a requirement of 110 volt. So what you will do, you will use a transformer. Okay, you will use a transformer, and this type of transformer you will use step down transformer. Step down transformer. And if in your home the voltage supply is 110 volt from the power station and you want this 220 volt, I am just giving the example. So what type of transformer you will use? Step up transformer you will use. Step up transformer. Okay. So according to the requirement, we use the transformers. Step up and step down. So now I will discuss the principle of the transformer, on which the transformer works, and working and construction of the transformer. Working and the construction of the transformer. So it is very simple. Basically, the transformer works on the principle of mutual induction. Transformer works on the principle of mutual induction. Mutual induction means, mutual induction basically is a property of two coils. When there is a change in one coil, okay, when there is a change in the current in one coil, there is an induced current in the another coil. There is an induced current in the another coil. This is known as the mutual induction. So before the working of the transformer and the construction of the transformer, we should know what is the solenoidal coil and what is the magnetic field due to that solenoidal coil. So this is the solenoid, suppose. Okay, this is the solenoid. This is a solenoid, and this is the magnetic field due to the solenoid. Okay, magnetic field due to the solenoid. And in solenoid the current is I. Solenoid, I have told you, in solenoid the current is I, and this is the direction of the magnetic field. So this magnetic field is axial. This magnetic field is axial magnetic field. Okay, and I have told you one more thing about the solenoid. If there is I current in the solenoid, then magnetic field inside the solenoid is equal to B is equal to mu naught into small n into I. Mu naught is the permeability of the free space and number of turns per unit length of the solenoid. I is the current flowing in the solenoid. So this is the magnetic, this will be the magnetic field in the solenoid. And remember, this magnetic field confined within the solenoid, okay, within the solenoid, and this magnetic field is axial. Okay, this magnetic field is the axial magnetic field. You can write here, magnetic field is axial. This thing is clear. And there is one more thing you should know, magnetic flux. I have told you many times, magnetic flux. Magnetic flux is represented by phi b, and magnetic flux is given by BA cos theta. What is theta? Theta is the angle between the magnetic field and the area vector. Okay, so theta is the angle between magnetic field and area vector. Area vector. So this is the requirement for the study of the uh, transformer, and you should know what is the mutual induction also. Okay. Okay. Now, see, this is the structure of the solenoid, not transformer. Basically, this white color thing. See this white color structure. First, see this white color. Only focus on this white color structure. We have taken a white color structure like this, and I will tell you what is this white color structure. We have taken the structure like this. Okay, we have taken the structure like this, and this structure is known as the soft iron core. Is known as the soft iron core. Soft iron core. This is soft iron core, and on this soft iron core, what we do? What we do? Uh, Here there is a winding like this of wire. Winding. This is known as the winding. Okay, and here also there is winding of wire like this. Okay, this part. See this part. Winding of wire like this. So this thing I have done here. Basically, this is a soft iron core, and on the soft iron core, here is winding, and here is winding. So basically, uh, there are two types of winding in case of the transformer, primary and the secondary winding. So this is the primary winding, this is the secondary winding. Primary winding and secondary winding. And here these are the magnetic field lines. So basically this is these windings, see, these windings is connected with an alternating voltage source. So means there will be the current in the winding, and this is it. And I have told you, in winding or in case of the solenoid, if there is a current, then there will be the magnetic field produced, and that magnetic field is axial. So magnetic field will be axial. For example, magnetic field due to this will be like this. Magnetic field will be like this. This will be the magnetic field produced by the winding. Okay, this is the magnetic field produced by the winding. Now you will say how this magnetic field, is it. Okay, so now you will say how these are the magnetic field lines due to this winding. Okay, due to this winding, these are the magnetic field line. But here is the soft iron core, and this soft iron core has a property to confine the magnetic field line within. Okay, so due to this, what will happen? Due to this, these magnetic field lines will be confined like this. Okay, confined like this, will be like this, and passes through these magnetic field line, or you can say crosses this winding also. Okay, so that is why this is the structure of the field line. Now I think you will get how I have made this structure. Basically this is due to the, okay, so no need of this. So basically NP is the number of turns in the primary coil. NP is the number of turns in primary winding, you can say primary windings. So you can write ns is the number of turns in the secondary winding. Finish. So basically this is the primary winding. This is the primary winding. And this is the secondary winding. This is the secondary winding. So primary winding, secondary winding. And what are these? These are the magnetic field lines. So basically these magnetic field lines are produced by the primary winding. But due to this soft iron core, these magnetic field lines are crossing this secondary winding also. Okay, crossing this secondary winding also due to this soft iron core. Okay, so basically generally the windings we take of copper. Winding means wire is of copper. So basically here this is the winding, and this winding is connected with an input voltage, and this input voltage is an alternating input voltage. So this is the symbol of the alternating input voltage. So this is the input voltage, means the voltage initially you are providing to the transformer. Now how the transformer transform this voltage? How the transformer transform this voltage? See, suppose you are providing some voltage, input voltage here to this transformer. Suppose EP is the voltage across the primary winding. EP is the voltage across the primary winding. Now you have supplied the voltage, and due to this voltage there will be the current in the winding, and due to the current there will be the magnetic field, or you can say the magnetic field line. And due to the soft iron core, the magnetic field line will also pass through the secondary winding. And one thing here I have told you, the magnetic flux, very important part, magnetic flux. So here these magnetic field lines are crossing the secondary winding also. So what is the meaning of the magnetic field lines crossing the secondary winding? Means there is a magnetic flux crossing the secondary winding, and this is an alternating voltage. So due to the alternating voltage, there will be the alternating current, and alternating current means the changing current. Okay, now see, this is the magnetic field. So this is the magnetic field. This is the magnetic field, and here is the alternating current. So you can say alternating current. This current is changing, magnetic field is changing. Okay, basically this magnetic field due to the primary winding is changing. Okay, so you can say the magnetic field here also the changing, because same magnetic field lines are going here also. So you can say here the magnetic field is changing due to the alternating current. And what happens when the magnetic field changes? See here, if this magnetic field will change, there will be the change in the magnetic flux. And what happens when magnetic flux linked with the coil or the winding will change? What happens, Matthew, when magnetic flux changes? When the magnetic flux linked with this winding will change, EMF will induce, na, according to the Faraday's law of electromagnetic induction. Okay, Matthew?
Okay, sir.
EMF will be induced, na? And that EMF will be induced here in the secondary winding, will give you the output voltage that you want. and this will be changed with the help of number of turns in the secondary winding that we will see. So basically this is the working of the transformer. Basically this is the working of the transformer. Okay, now see, I have told you the magnetic flux is given by B dot A or VA cos theta, and this magnetic flux across this winding or across this winding is changing. Magnetic flux is changing. So this magnetic flux is changing. Why changing? Due to the change in the magnetic field, due to the change in the current, because current is the alternating. Now you can see number of magnetic field line crossing. See, this is one coil. Take any one coil. Take any one coil. I am taking this one coil. This is a coil, na? Circular coil. Here is this. Take this coil. So can you tell me number of magnetic field line crossing this coil and number of magnetic field line crossing this coil are equal? Okay. So you can say that magnetic flux linked with each coil of the primary winding is equal to the number of magnetic field lines or magnetic flux linked with the each coil of the secondary coil. Okay, so here I have written magnetic flux linked with each turn of the primary winding is equal to the magnetic flux linked with the each turn of the secondary winding. Okay, so you can see here number of, see, take this coil and see here I have shown three magnetic field lines are crossing this area of this coil. Here also three magnetic field lines are crossing this area, and number of magnetic field line crossing the area is equal to the magnetic flux. So basically for the each turn of the primary coil, for the each turn of the secondary coil, the magnetic flux will be same, and that is represented by phi. So phi is basically the magnetic flux linked with each turn of the primary coil and each turn of the secondary coil. And why this is equal, you can see here. Okay, so now if I want the total magnetic flux in the primary windings, total magnetic flux, total magnetic flux in primary winding. So suppose total magnetic flux in the primary winding is phi suffix p. So now I am calculating total magnetic flux in the primary winding. See, this is the primary winding and number of turns in the primary winding is this, and in one turn of the primary winding the flux is phi. So total flux in the primary winding will be phi into np, or you can say np into phi. Number of turns in the primary winding into flux linked with the each coil of the primary winding. Now we can also find total magnetic flux in secondary winding. Secondary winding, suppose this is represented by phi suffix s. This is given by, can anyone tell me what is the total magnetic flux in the secondary winding? Nafisa? It is so simple. See, phi is the magnetic flux linked with one coil of the winding, and number of turns are ns. So simply you have to multiply ns with phi. Okay, you will multiply ns with phi. Okay. Now EMF induced, as the flux is changing here also, flux is changing here also. So if the flux is changing with respect to the winding, so in winding there will be the induced EMF. So induced EMF in the primary winding. Induced EMF in primary. Suppose induced EMF in the primary is represented by E suffix P. So induced EMF in the primary is equal to, according to the Faraday law of electromagnetic induction, change in the magnetic flux in the primary winding divided by dt. Okay, so this will become minus d by dt. And what is phi p? Phi p you can see from here, np into phi. This is np into phi, and number of turns will remain same in the primary winding, so it will become minus np d phi by dt. d phi by dt. Okay. Now induced EMF in the secondary winding. Induced EMF in the secondary winding, ES. Oh, Matthew, what will be the induced EMF in the secondary winding?
So it'll be d phi p, no, d phi
Yes,
s by
very
dt.
good, very good, very good. D phi S by dt minus d by dt of, put the value of phi S. Phi S is ns into p, ns into ns into phi. So number of turns you cannot change, na? Number of turns, once you have done the winding, then means number of turns fixed. Okay, so we cannot change that. So number of turns will be constant. We will take out of the differentiation. It will become d phi by dt. Okay, now can we do this ES divided by EP? So basically your ES is equal to minus of ns d phi by dt minus of ns d phi by dt, and EP is minus of np d phi by dt. Okay, so now see, this d phi by dt and this d phi by dt is cancel out, minus and minus will be cancel out. So EMF in the secondary winding divided by EMF in the primary winding is equal to number of turns in the secondary winding divided by number of turns in the primary winding. This is the relation, first relation we got. This is the first relation. Now with the help of this expression, we can just decide the number of turns in the step up transformer and step down transformer. If the transformer is suppose step up means what you want? You want the secondary voltage or voltage across the secondary coil must be greater than the voltage across the primary coil. Okay, this is you want. So now you can see here, ES divided by EP is greater than 1. And what is ES by EP? NS by NP. So you can write NS by NP is greater than 1. So you can say that number of turns in the secondary coil must be greater than the number of turns in the primary coil. So this is the case of the step up transformer. For the step up transformer, The number of turns in the secondary winding must be greater than the primary winding. For the step down means you want to decrease the voltage, means voltage at the secondary must be less than the voltage at the primary. So it means that number of turns in the secondary must be less than the number of turns in the primary. Okay. So basically, what you are doing, you are applying some input voltage. Basically, what you are doing, you are supplying some electrical power. You are applying some electrical power here, and here you are getting some electrical power. Basically, electricity, you are providing the electricity na, to the transformer, and here also you are getting some electrical power. So if the power you have applied or power you have supplied is equal to the power you are getting at the output, both are equal, then you can say your transformer is 100% efficient. But in this world, nothing is 100% efficient. Okay. So transformer also cannot be 100% efficient, but we study for ideal transformer. So ideal transformer is basically a transformer having 100% efficiency. So ideal transformer. So what is the meaning of the ideal transformer? 100% efficient transformer. 100% efficient. So 100% efficient means power input meet at the primary winding, you are giving the power input and you are getting the power at the secondary winding, that is power output. What is the power input? Power input means current into voltage. What is the current in the primary winding? IP. Suppose IP is the current in the primary winding and voltage is EP. So it will be IS, current in the secondary winding, voltage in the secondary winding. So this from here you can just say that ES by EP is equal to IP by IS. This is another relation for ideal transformer only. For ideal transformer only. For ideal transformer. And this expression is not always valid. Not always valid. So two relation we have. First is this, another is this. So for ideal transformer, you can write this relation ES by EP is equal to NS by NP. This relation is always valid. When you will write that IP by IS, so this relation is valid for only ideal transformer. This relation, okay, and this relation also, this and this also. What is IS and IP? IP is the current in the primary winding. IS is the current in the secondary winding. So I think I should write here. Here I am writing. IP is current in primary windings, and I suffix S is the current in secondary windings. Current in the secondary windings. Now, very simple question based on this. We have very simple question. This is the question we have. Oh. Okay. So basically, this is a transformer. This is a transformer, and this is an ideal transformer. This is an ideal transformer. So if this is an ideal transformer, so for this transformer means this expression will be valid. ES by EP is equal to NS by NP is equal to IP by IS. This is valid. Okay, so it is given that this information is given. Number of turns in the primary, this is the primary winding of the transformer, this is the secondary winding of the transformer. And this is the ideal transformer given in the question. Input is given. Input means 220 volt is the voltage at the primary winding, and 10 ampere current will be there at the primary winding. We have to find the secondary current and the secondary voltage. Means voltage across the secondary winding and current across the secondary winding. Okay. So you can use first this relation. You can use first this relation. Basically, what is given to you? Input means at the primary winding given. Okay, so means voltage across the primary winding is given as 220 volt. Okay, and current at the primary winding is given as 10 ampere. This is given, and number of turns for the primary winding is equal to 100, and number of turns for the secondary winding is equal to 200. Now use this expression. ES by EP is equal to NS by NP. ES, we have to find ES. Okay, we have to find ES because see here ES we want to find. This is ES, voltage at the secondary winding. What is EP? 220 volt. What is NS? 200. What is NP? 100. This will be cancel out. It will be 2. So when you will multiply 220 with 2, it will become voltage across the secondary winding is equal to 440 volt. 440 volts. First answer is this. Second answer you can find with the help of this expression. Number of turns in the secondary winding 200, number of turns in the primary winding 100, current in the primary winding is 10 ampere, current in the secondary we want. This is 2 and this is 2, 5 are 10. So current in the secondary winding is equal to 5 ampere. Current in the secondary winding is equal to 5 ampere. Got it? Matthew, Nawal and Nafisa, how to solve my
Yes, sir.
question?
Yes, sir.
Yes, sir.
So write down. When completed, you can ask me to scroll down. Matthew, should I scroll down?
Wait, sir. Wait.
Okay. Completed, Nafisa?
Done, sir.
Yes, sir.
Okay. So draw this. Draw two rectangles. Okay. Concentric rectangles. And after that, windings there, primary winding, secondary winding, and show the magnetic field line like this.
Done, sir.
Nafisa and Nawal completed. Should I scroll down?
Yes, sir.
Scroll down.
Wait, sir.
Okay.
Yes, I can scroll now.
Completed? Nawal, completed?
Yes, sir.
Matthew and Nafisa?
Just a second, sir. I'm just writing the last equation.
Okay.
Yes, done.
Nafisa, completed?
Yes, sir.
Okay, so write down this also.
Done, sir.
Okay. Nafisa completed. Nawal completed.
Yes, sir.
So after
Yes.
this, we will discuss the energy losses in transformer. Okay, so before the energy losses, there is one more thing that I want to add. Basically, in practical transformer, you are supplying the input power that is not equal to in actual the output power you are getting. Why? Because there are some losses in the form of the heat also. Okay, you can take the example of your laptop. The energy, electrical energy you are supplying, not that electrical energy is totally utilized. Some of the energy is going in heating process, or you can say in the form of the heat across the resistance. So basically input power is always greater than the output power in case of the practical transformer. So we can write this expression. This expression is 100% valid. For that we define the efficiency. Efficiency is basically output power divide by the input power, output power, input power formula, you know, multiply by 100, you will get. Now there will be the energy losses in the transformer. First energy loss is, these are the magnetic field lines. So there are the magnetic flux leakage also. These magnetic field lines in case of solenoid are not exactly are not like this. Okay, magnetic field lines in this case, in case of the solenoid, are like this exactly. When you will see, basically magnetic field line will be like this. This is like this, like this. Okay, so due to this shape of the magnetic field lines, there will be some flux leakage. Okay, there will be some flux leakage here. Okay, so first loss is your flux leakage. And how to minimize the flux leakage? We use the soft iron core, so that the soft iron core has a tendency or has the ability to attract the magnetic field lines. Okay, so there will be the minimum flux leakage. Another is the winding resistance. Another will be the winding resistance. This is very simple. This yellow color is the wire, and this yellow color wire is the winding, and winding is the wire. So wire will always have the resistance. There is no wire in this world having the zero resistance. So there will be always the resistance, and due to the resistance, there will be the heat loss. I square RT, heat loss. Second loss is this energy loss in the form of the heat. Okay, energy loss in the form of heat. How to minimize? Decrease the resistance of the winding. How you will decrease the resistance of the winding? There are several ways. Basically, to decrease the resistance of the winding, either you should use the winding of copper. Either you should use the winding of copper, because copper has the least resistivity. Okay, copper has the least resistivity. Okay, and use thick copper wire. Thick copper wire means area of the cross section of the copper wire is large. If the area of the cross section of the copper wire is large, see, resistance is given by rho L by A. And if area will be large, then resistance of the winding will become reduced. If the resistance will become reduced, okay, if resistance will be less, okay, then heat loss will be less. Okay, from this formula, heat loss will be less. So we use thick copper wire on that side of transformer where the current is high. Basically, copper is a precious, you can say, costly metal. So that is why we cannot make the whole transformer as of copper. Okay, so we use copper, thick copper wire on the side of the transformer where the current is very high. Okay, on that side. And another is the hysteresis loss. What is the meaning of the hysteresis loss? Basically, here this is the alternating current, and alternating current is increasing, becomes zero, and then decreasing, and after that also becomes zero. Basically, alternating current changes with time. Sometimes it will be zero, sometimes it will be maximum. Okay, so what happens? Due to that, there is a magnetization. There is a magnetization in the winding, or demagnetization in the winding. And due to the magnetization and demagnetization in the winding, there is a loss known as the hysteresis loss. Alternating current changes, we know that, due to which magnetic field changes. We know that if the current change, the magnetic field change. Continuous magnetization and demagnetization takes place, hence energy losses. What is the solution? Use soft iron. Now, eddy current losses. Basically, eddy current earlier was in your syllabus of electromagnetic induction, now removed. So basically, I am telling what is the eddy current. Basically, eddy current is a result of the electromagnetic induction. Okay, whenever there is a change in the magnetic flux linked with the bulk piece of the material. What is the meaning of the bulk piece? Suppose this is any steel piece of the steel, and magnetic flux is changing. So there will be the eddy current produced in this bulk piece. Okay, this is not a coil, this is a bulk piece of something. Okay, so basically what happens in case of the transformer, what happens from the starting? Current will change continuously. Why? Because current is alternating. Current change current is changing continuously. Why? Because the current is alternating. Alternating current. Current is changing continuously. Okay, why? Because the current is alternating. What happens if the current will change? Mu naught n I. If this current will change, the magnetic field will be changed. Okay, so we can write magnetic field will change. Now phi is equal to BA cos theta. So what happens when the magnetic field will change? So here see, this magnetic field will change means magnetic flux will change. So we can say magnetic flux will change. Okay. Now change in magnetic flux will give you the EMF. So magnetic flux change will give you the EMF. So EMF will be induced. So basically two types of EMF will be induced. First, induced EMF will be in the windings, that is in copper wires. Okay, that we were discussing. In these windings there will be the induced EMF, and another induced EMF will be across the soft iron core, across the bulk of the across the material of the soft iron core, and due to that induced EMF in the soft iron core there will be the eddy currents. There will be the eddy currents. Okay. Okay, so basically this will another induced EMF will be the material of the core, soft iron core, and eddy current will be produced. Okay, so this is the soft iron core. This is the soft iron core. This is a core. Basically, in this core, this is the eddy current. This eddy current is in the circular form like this. Okay, this is the eddy current like this. So eddy current are like this. So due to the eddy current, what will happen? There will be the resistance. This eddy current is inducing in the material, and this material will have the resistance. And from this formula, you can see there is a heat loss. There is a heat loss. From this formula, ID square RT, and R is the resistance of the material in which the current is inducing. So there will be the heat loss due to the eddy current. How to minimize the eddy current? Use laminated cores with insulating liquid in between. Laminated cores means we have to use the, just wait a minute. So laminated cores means, suppose this is the one core and another core and another core. Like the pages of your copy, you will use the laminated cores. Okay. So for that, what will happen? The eddy current will reduce so that the energy loss will be reduced. Okay. Now you can note down, all of you. And this chapter is finished now. Nafisa, Nawal, and Matthew, do you have any doubt regarding this?
No, sir.
No, sir.
Okay.
No,
So what
sir.
about step up and step down transformers?
Hmm? Step up.
We discuss step up and step down.
Actually, I have discussed that a step up is a transformer which basically increases the voltage. Okay. In the starting, I have
Yeah,
told you
okay.
now
So,
what is in the
yeah, yeah,
starting.
sir. I just thought that we'll discuss about it more other than this. But okay, fine, it's fine, sir. No problem.
Okay. Ask me to scroll down when completed. Okay. And do revision your notes.
Done, sir. You can scroll down.
Okay.
Done, sir.
So energy losses in transformer, you can just learn this. What are the type of the energy losses like flux leakage, resistance of the winding, hysteresis losses, and eddy current losses. One point you will write, you will get the required marks in exam. And this sign of down arrow is representing resistance decreases to decrease the resistance. And this upward arrow means area is increasing.
Done, sir.
Nawal and Nafisa,
Yes, sir.
completed?
Yes, sir.
So write down this also, and this is the I will say from my side this chapter is finished. Okay, so now it depends upon you how many times you are revising and how much time you are giving to this chapter. Okay, and that will decide how much marks you will get in the exam. And I have tried my best to explain this all the concepts, because I know that these concepts are little bit complex, but I always try to simplify the concept for the students. Okay, so here in this chapter all the things are happening. Why is the production of why the generation of the electric alternating current? Because of the change in the magnetic flux. Changing magnetic flux is the reason. And this is founded by the Faraday.
Done, sir.
Yes,
Okay,
sir.
so okay, so okay, so this chapter is finished. So have I completed the resonance now? Matthew and Nawal and Nafisa? Resonance?
Okay, wait, sir. Let me check.
Resonance. This is resonance. This is. Have I completed this in your class?
I don't think so, sir.
Hmm? Do you have the notes? Okay, no problem. If this topic is not completed, then we will first complete this topic in the next class and we will move. Okay, no
Okay, sir.
problem. Don't worry. Okay, all of you, we will meet in the next class.
Thank
Till
you, sir.
then, okay, revise your notes properly. If you have any doubt regarding this, you can ask me.
Okay, sir. Thank you, sir.
Okay, okay.